You know, when you look around, from the phone in your hand to the DNA inside you, there's one element that forms the backbone of it all: carbon. Today we're going to unpack the simple but brilliant trick it uses to build pretty much everything. Let's dive in.
So what's the big deal with carbon anyway? I mean, it's not even the most common element out there. But it forms millions and millions of compounds, way more than anything else. The secret? Well, it's all in how it connects with other atoms.
To really understand carbon's genius, we first have to understand its big problem. See, every atom out there just wants to be stable, and that usually means having a completely full outer shell of electrons. But for carbon, getting there is a real headache.
And that whole headache comes down to this one number: 4. Carbon has exactly 4 electrons in its outermost shell, its valence shell. And that number, 4, puts carbon in a really tricky spot.
Yeah. See, to get that full shell, atoms usually either gain a few electrons or lose a few. Easy enough. But carbon, with its 4, is stuck right smack in the middle. It needs to gain 4 more to fill up or lose all 4 to empty out. And it turns out both of those are terrible options.
Let's break down why. Okay, if carbon tries to grab 4 extra electrons, its little nucleus, which only has 6 protons, just can't hold on to 10 electrons. It's too much. That's unstable. On the flip side, trying to rip 4 electrons away from it, that takes a massive amount of energy. So for carbon, making ions is just not going to happen. Instead, it figured out a much better way. Instead of giving electrons away or stealing them, carbon does something totally different. It finds a solution that's way more elegant and, frankly, way more powerful. It learns to share.
And this whole sharing plan is called a covalent bond. Think of it like a chemical agreement, where 2 atoms both put some electrons into a shared pool. By sharing, both atoms get to count those shared electrons as their own, and boom, they both get that stable, full shell they've been wanting, without all the drama of becoming an ion.
So to really get a feel for how this works for carbon, we're going to start with some simpler examples first. You'll see how this one idea of sharing builds everything from simple gases all the way up to us. Let's start with the simplest atom there is: hydrogen. Each one has 1 electron, but it really wants 2 to be stable. So 2 hydrogen atoms get close, they each put their 1 electron into the pot, and they form one shared pair. That's a single covalent bond. Now both atoms are stable, everybody's happy.
Okay, now let's level up to oxygen. Each oxygen atom needs 2 more electrons to get stable. So what do? Well, 2 oxygen atoms each share 2 of their electrons, which forms 2 shared pairs. And that creates a strong double covalent bond.
And you can probably guess where this is going with nitrogen, right? Each atom needs 3 electrons, so 2 of them get together and they share 3 pairs of electrons. This forms an incredibly strong triple covalent bond, which, by the way, is why the nitrogen gas in our air is so stable.
All right, so we've got our basic toolkit now: single, double, and triple bonds. We see the pattern. Sharing creates stability. So with that in our back pocket, we can finally go back to carbon and see how it uses these very same tools to solve its big problem. So remember those 4 outer electrons? Well, that means carbon can form 4 separate covalent bonds. Take methane, CH4. 1 carbon atom shares its 4 electrons with 4 different hydrogen atoms. Each hydrogen gets its full shell, and the carbon, because it's sharing with all 4, gets its full outer shell of 8. It's a perfect, totally stable little molecule.
Now, this sharing strategy doesn't just build molecules. It gives them some really unique properties. Properties that are totally different from ionic compounds, like good old table salt.
Just look at these numbers for a second. These carbon compounds have incredibly low melting and boiling points. Methane boils at just 111 Kelvin. That's minus 162 Celsius. It happens because the forces holding one molecule to another molecule are actually pretty weak. And this is a really key idea. The covalent bonds inside the methane molecule, they're super strong. But the forces of attraction between two separate methane molecules, those are weak. So when you boil methane, you're not breaking the strong bonds inside, you're just easily pulling the molecules apart from each other. And here's another huge difference: electricity. Ionic compounds, when they dissolve, they break up into charged ions that can carry a current. But covalent compounds, they don't do that. They don't form ions, so there are no free-floating charges to carry electricity. They are poor conductors.
Okay, so we've seen carbon's problem, and we've seen its incredibly elegant solution. But now it's time for the big finale. How does this simple act of sharing allow carbon to become the architect of life itself?
The answer is a property with a cool name: catenation. And this is carbon's true superpower. It's the ability to form long, strong, and really stable bonds with other carbon atoms. That carbon-carbon bond is just exceptionally stable, and that allows it to build massive, complex structures. This ability to just keep linking up with itself means carbon can form an almost infinite variety of shapes and structures. It can build long, straight chains like you find in fats, it can make branch chains, and even complex rings like the ones in sugar. It really is the ultimate molecular Lego brick. You can build almost anything with it. So let's just bring this all home. Carbon had a problem. It was stuck with 4 outer electrons. That forced it to find a clever solution: sharing. And that simple act of sharing, that covalent bond, is what allows carbon to create the amazing chains, rings, and branches that are the literal foundation for every single organic molecule, from simple stuff like methane all the way to the DNA that makes you, well, you.
And that kind of leaves us with one last thought, doesn't it? We've seen how this one simple rule, sharing electrons to get stable, is the basis for the entire chemistry of life. So it just makes you wonder, what other incredible and complex structures has nature built using that same beautifully simple principle?